Physics is not something that happened in laboratories. It happened everywhere, all at once, the moment the universe began. Humans just slowly noticed. Tonight, 101 facts, one story. Let's start. Fact 1. The oldest physics observation we know of was not written in a book. It was built into the ground. Around 5,000 years ago, people arranged enormous stones in a circle so precisely that on the longest day of the year, the rising sun aligns perfectly with the main entrance. That place is Stonehenge. Whoever built it understood something fundamental, that the sun moves in a predictable arc, that shadows fall in predictable directions, that the universe follows rules. They had no word for physics, no equations, but they were observing the world carefully, noticing patterns, and building something that captured those patterns in stone. Before Stonehenge, humans tracked shadows with sticks pushed into the ground. The length of the shadow told you the time of day. The direction told you which way was north. That understanding is where the entire story begins. And that leads us into fact 2. For thousands of years, humans noticed that things fall. Nobody asked why. It was just how the world worked. Then around 350 BC, Aristotle decided to actually think about it. His answer was wrong, but asking the question at all was important. Aristotle believed objects fall because they are trying to reach their natural place. Heavy things belong on the ground. Light things made of air and fire belong upward. He also believed heavier objects fall faster than lighter ones. This was wrong. A cannonball and a feather dropped from the same height do not reach the ground together, but that is because of air resistance, not weight. In a vacuum, they fall at exactly the same rate. Aristotle was wrong in almost every detail, but he was the first person to treat the falling of objects as a question worth answering. That instinct changed everything that came after. Fact 3. Around 250 BC, Archimedes stepped into a bath. He had been given a problem by the king of Syracuse. The king suspected his goldsmith had mixed silver into a gold crown. As Archimedes lowered himself into the bath, he noticed the water level rise. The water rose according to his volume, not his weight. If he could measure how much water the crown displaced, he would know its volume. Knowing both weight and volume, he could calculate density. Gold has a specific density, silver has a different one. A crown mixed with silver would fall between the two. The story says he leapt from the bath shouting Eureka, meaning I have found it. What matters is the insight. An object submerged in liquid displaces liquid equal to its own volume. This is why ships float. This is why you feel lighter in water. The first recorded moment where someone solved a real physical problem through deliberate reasoning. On to fact 4. Archimedes did not stop at bathtubs. One of his most important discoveries was the lever. People had been using levers for thousands of years before him. A branch wedged under a rock is a lever. A seesaw is a lever. But Archimedes was the first to describe exactly how a lever works in precise mathematical terms. The further from the pivot point you apply a force, the less force you need to move a given weight. Double the distance, halve the effort. Archimedes understood the implications so clearly that he supposedly said, "Give me a place to stand and a long enough lever, and I will move the earth." He was not being poetic. He was doing the calculation. The principle of the lever is the foundation of every crane, every pair of scissors, every bicycle gear system ever built. A man in Syracuse, 2,300 years ago, worked out the rule that still runs through every piece of mechanical engineering on Earth. Fact 5. Around 400 BC, Democritus proposed one of the most radical ideas in the history of science. If you take any piece of matter and keep cutting it in half, you will eventually reach a piece so small it cannot be cut further. He called this smallest possible piece atomos, meaning uncuttable. Everything in the universe, he said, is made of these tiny particles moving through empty space. Different materials feel different because their atoms have different shapes. Water atoms are smooth and round. Iron atoms are hard and jagged. This was philosophy, not experiment. Democritus had no way to test it. He he was ignored for most of the next 2,000 years. Then, in the early 1800s, John Dalton revived the idea with experimental evidence. In the early 1900s, physicists confirmed atoms are real. For a man working with no instruments in 400 BC, he was remarkably, almost unsettlingly close. And that brings us to fact 6. Long before compasses or satellites, sailors navigated using the night sky. One star appears almost perfectly still. Polaris, the North Star, sits almost directly above the Earth's North Pole. As the Earth spins, every other star traces a circle around it. A sailor who could find Polaris always knew which direction was north. The angle between Polaris and the horizon also revealed latitude. The higher it sits, the further north you are. At the North Pole, it sits directly overhead. At the equator, it sits on the horizon. Separately, Chinese navigators around 200 BC discovered that certain iron-rich rocks called lodestones always point the same direction when suspended freely. They were detecting the Earth's magnetic field generated deep in the planet's molten iron core. Two completely independent physical phenomena, one star that barely moves and rocks that always point the same way, both quietly telling sailors where they were. Fact 7. There is a famous story about Galileo climbing the Leaning Tower of Pisa and dropping two cannonballs of different weights simultaneously. Both hit the ground at the same time. Aristotle was wrong. Whether Galileo actually did this at the Tower of Pisa is debated. He may have used a different building. He may have done it only as a thought experiment. But what is not debated is what he proved. Through careful experiments, rolling balls down inclined planes and timing their descent, Galileo established that all objects accelerate at the same rate under gravity regardless of mass. The only reason a feather falls slower than a cannonball is air resistance. Remove the air and they fall identically. This was demonstrated on the moon by astronaut David Scott during Apollo 15 in 1971. He dropped a hammer and a feather side by side in the lunar vacuum. They hit the surface together. Galileo had been right 300 years before anyone could check. And next, fact 8. In 1609, Galileo heard that a Dutch spectacle maker had built a device that made distant objects appear closer using lenses in a tube. Galileo worked out the optics himself, built his own version, and pointed it at the sky. He saw that the moon had mountains and craters. He saw that the Milky Way was not a cloud, but countless individual stars. Then he saw 4 small points of light near Jupiter. He watched them night after night. They moved in a regular pattern around Jupiter. They were moons orbiting Jupiter, not Earth. This directly threatened the idea that everything in the universe revolves around the Earth. Here were 4 objects that clearly did not. Galileo published his findings. The church was not pleased. He spent the last years of his life under house arrest for refusing to retract what his telescope had shown him. Fact 9. Before the telescope, before any great discovery, there was a chandelier. Galileo was sitting in the Cathedral of Pisa as a young man, watching a large lamp swinging overhead. He noticed something. The lamp seemed to take the same amount of time to complete each swing, regardless of how wide the swing was. A large swing and a small swing took the same duration. He timed it against his own pulse, the only clock he had. He was right. This property, that a pendulum's period depends on its length but not on the size of its swing, is called isochronism. Galileo immediately understood the implication. A pendulum could be an extremely reliable timekeeper. Christian Huygens built the first working pendulum clock in 1656, accurate to within 15 seconds per day. Navigation, astronomy, scientific experiment, all required precise timekeeping. All of that precision traces back to Galileo sitting in a cathedral watching a lamp and asking the right question. Moving on to fact 10. For centuries, astronomers assumed planets moved in perfect circles. Circles were geometrically pure. It seemed right that heavenly bodies should follow them, but the observations never quite matched the predictions. Small errors kept appearing. Johannes Kepler spent years trying to make circles fit the data. They never fit perfectly. Finally, he tried a different shape, an ellipse. When Kepler placed the sun at one focal point and let the planet travel in an ellipse, everything matched. Not approximately, exactly. He published his first two laws in 1609 and his third in 1619. Planets move in ellipses with the sun at one focus. A planet moves faster when closer to the sun and slower when further away, and the time a planet takes to complete one orbit is mathematically related to its distance from the sun in a precise and consistent way. Kepler believed he had uncovered the geometric language God used to design the solar system. Whether or not that is true, he had written the first accurate mathematical description of how planets actually move. And here is fact 11. Kepler could not have done any of it without data he did not collect himself. That data came from a Danish nobleman named Tycho Brahe. Tycho lost part of his nose in a duel over an argument about mathematics and wore a metal prosthetic for the rest of his life. He kept a tame elk as a pet. The elk died falling downstairs after drinking too much beer. But the serious work of his life was spending 20 years making the most precise naked-eye astronomical observations ever recorded. Before the telescope existed, he measured the positions of planets and stars night after night with specially built instruments, achieving accuracy about twice as precise as anything done before. When Tycho died in 1601, his data passed to Kepler. The precision of those observations was what allowed Kepler to notice that circles did not fit. The tiny discrepancies only showed up because the data was good enough to reveal them. Tycho never knew what his life's work had made possible. Fact 12. For most of human history, nobody knew whether light traveled instantaneously or at a finite speed. In 1676, a Danish astronomer named Ole Romer became the first person to measure it. He was observing Io, one of Jupiter's moons, which disappears behind Jupiter at very regular intervals. He noticed something odd. When Earth was moving toward Jupiter, Io's eclipses happened slightly earlier than predicted. When Earth moved away, they happened slightly later. Romer realized this could only mean light takes time to travel. When Earth was closer, the light arrived sooner. When further away, it arrived later. From this timing difference, he calculated a speed for light that was remarkably close to the correct value, off by about 25% due to imprecise measurements of Earth's orbit. But he was right about what mattered. Light is not instantaneous. It has a speed. The scientific establishment was largely skeptical. It took 50 years and a separate measurement before the idea was widely accepted. Romer was right the whole time. And that brings us to fact 13. Throughout everything we have just covered, nobody was doing something called physics. The word barely existed in its modern sense. Galileo called himself a philosopher and mathematician. Kepler saw his work as uncovering divine geometry. Newton, who we will come to very shortly, called what he was doing natural philosophy. The people building our understanding of the physical world were philosophers, mathematicians, astronomers, and priests. Physics, as a distinct discipline with its own identity, came much later, but the work itself, the measuring, the testing, the insisting that the world must make sense and that careful observation can reveal how, that was already fully underway. Fact 14. The apple story is probably true, sort of. Newton himself told it multiple times in old age. Sitting in a garden, he saw an apple fall and began wondering why it fell straight down rather than sideways or upward. What made that direction special? The insight that followed was not simply that gravity exists. Everyone already knew things fell. The insight was that the force pulling the apple downward and the force keeping the moon in orbit around the Earth were the same force. The moon is essentially falling toward the Earth continuously. It just also has enough sideways motion that it keeps missing. Newton calculated what the strength of gravity would need to be at the moon's distance to keep it in its orbit. Then he calculated what the strength of gravity would need to be at the Earth's surface to make an apple fall at the rate it does. They matched. One force, one mathematical rule, operating identically on an apple in a garden and on the moon 250,000 miles away. That single realization unified the physics of the ground and the physics of the heavens for the first time in history. And next, fact 15. Newton's 3 laws of motion are the foundation of classical physics. Stated simply, they are these. First, an object at rest stays at rest, and an object in motion stays in motion unless something pushes or pulls it. Second, force equals mass times acceleration. Third, for every action, there is an equal and opposite reaction. These sound simple. Their consequences are enormous. The first law means that motion does not require a continuous push, which contradicted everything Aristotle had said. The second law gave engineers a precise mathematical tool for calculating exactly how much force is needed to move any object at any desired acceleration. The third law explains how rockets work. The engine pushes gas backward. The gas pushes the rocket forward. There is no air in space to push against. None is needed. These 3 laws govern the design of every ship, every cannon, every bridge, every engine built for the next 200 years. They still govern most engineering today. When Newton published them in 1687 in his book Principia Mathematica, he did not just describe how things move. He gave humanity a machine for predicting the physical world with precision. Fact 16. When Newton sat down to work out the mathematics of gravity and motion, he ran into a problem. The mathematics he needed did not exist. Existing tools could handle straight lines and simple curves. They could not handle quantities that changed continuously, like the speed of a falling object at any given instant or the area under a curved path. So Newton built the mathematics himself. He called it the method of fluxions. We call it calculus. He developed it in the mid-1660s during a period when Cambridge University was closed due to plague, and he had retreated to his family home in Lincolnshire with essentially nothing to do. He solved some of the most important problems in the history of physics and invented an entirely new branch of mathematics to do it. Then he told almost nobody for over 20 years. His reluctance to publish was almost pathological. He feared criticism and dispute above almost everything. Calculus eventually became public through a long and bitter argument about whether Newton or the German mathematician Leibniz had invented it first. Both had, independently, but the delay in sharing it cost science decades of progress it could have had sooner. Moving on to fact 17. Newton bought a prism at a fair in 1666, reportedly out of pure curiosity. He took it into a darkened room, let a narrow beam of sunlight in through a small hole, and passed the beam through the prism. White light spread into a full spectrum of colors on the wall: red, orange, yellow, green, blue, violet. Newton then passed the colored light through a second prism and showed that the prism was not adding color to the light. It was separating colors that were already there. White light is not a pure, simple thing. It is a mixture of every color simultaneously. This was a clean, elegant, important discovery. What followed was less clean. Newton published his findings and immediately entered one of the most vicious disputes of his career. The English physicist Robert Hooke insisted light was a wave. Newton believed it was made of particles. They argued bitterly for years. Newton was wrong, and also not entirely wrong. Light behaves as both, depending on how you look at it. But that resolution would not come for another 2 centuries. For the moment, it was simply 2 brilliant men who deeply disliked each other arguing about something neither could fully prove. And that brings us to fact 18. Behind all of this, behind the laws and the calculus and the prisms, was a man who was in many ways extremely difficult to know. Newton had almost no close friendships throughout his life. He ate irregularly, forgot meals entirely when absorbed in work, and could go days without speaking to anyone. He spent more years of his life writing about theology and biblical prophecy than about physics. He was obsessed with alchemy, the attempt to turn ordinary metals into gold, and conducted thousands of secret experiments that went nowhere. He had a nervous breakdown in 1693 from which he took years to fully recover. He served as a member of parliament and reportedly spoke only once to ask an usher to close a drafty window. He never married. Most historians believe he died a virgin, the man who gave the world its most powerful description of physical reality was himself almost entirely removed from ordinary human experience. His genius and his isolation seem to have been two sides of the same thing, an almost total inability to be distracted from the interior world of his own mind, where the mathematics lived and where he preferred to stay. Fact 19. Temperature is not what it feels like. It feels like a property of objects, something they simply have, like color or weight. But temperature is actually a measure of motion. Everything is made of atoms. Those atoms are never still. They vibrate, bounce, and move constantly. The faster they move, the higher the temperature. When you touch something hot, what you are feeling is the atoms in that object colliding with the atoms in your skin and transferring their motion to them. Heat is just kinetic energy moving between particles. This means there is a lowest possible temperature. If temperature is atomic motion, then the coldest possible state is when atoms stop moving entirely. That temperature is minus 273.15 degrees Celsius, known as absolute zero. Nothing in the universe has ever reached it. Nothing ever will, for reasons we will come to shortly. But the concept reframes what temperature actually is. Not a vague quality of warmth or coldness, a precise measurement of how fast the invisible particles inside everything are moving at any given moment. And next, fact 20. Thermodynamics is the branch of physics that deals with heat and energy. It has three main laws, and they are sometimes summarized in a darkly humorous way. You cannot win. You cannot break even. You cannot quit the game. More precisely, the first law says energy cannot be created or destroyed, only converted from one form to another. Every engine, every machine, every living body is just moving energy around. None of it makes new energy. The second law says that whenever energy is converted from one form to another, some of it is always lost as heat that cannot be recovered and used again. No machine is perfectly efficient. None ever can be. Every process in the universe bleeds a little energy into useless heat. The third law says that as temperature approaches absolute zero, the disorder in a system approaches a minimum. You can get colder and colder, but you can never actually reach absolute zero because doing so would require removing every last trace of energy, which itself requires energy. The universe has rules. These are three of the hardest ones. Fact 21. Entropy is one of the most important concepts in physics, and also one of the easiest to feel in daily life. Your room gets messy on its own. It never cleans itself. A dropped glass shatters into pieces. The pieces never spontaneously reassemble into a glass. Milk stirred into coffee spreads through the cup. It never unspreads. Entropy is the measure of disorder in a system, and the second law of thermodynamics says it always increases over time in a closed system. There are vastly more ways for things to be disordered than ordered. A tidy room requires every object to be in one specific arrangement. A messy room can take millions of different forms. The universe drifts toward disorder simply because there are more ways to be disordered than ordered. This has a profound implication for time itself. The laws of physics work equally well forward and backward in time, but entropy only increases in one direction. Some physicists believe this is the actual reason time feels like it moves forward. The arrow of time may simply be the arrow of increasing disorder. Moving on to fact 22. The steam engine did not arrive because someone sat down and worked out the thermodynamics first. It arrived through tinkering, trial, and enormous commercial pressure. Thomas Newcomen built a working steam engine in 1712 to pump water out of flooded mines. It worked, but it was spectacularly inefficient, wasting most of its energy reheating a cylinder that it had just cooled down. James Watt, a Scottish instrument maker, was asked to repair a model of Newcomen's engine in 1763. He immediately saw the problem and redesigned it with a separate condenser, keeping the main cylinder hot at all times. His version used a fraction of the coal. The improved engine spread rapidly through mining, then textile manufacturing, then transportation. The Industrial Revolution, which reshaped human civilization, ran on the thermodynamic improvements James Watt made to a machine he had been handed to fix. He did not set out to change the world. He was just trying to stop a cylinder from cooling down unnecessarily. And here is fact 23. Absolute zero is minus 273.15 degrees Celsius, or zero on the Kelvin scale. It is the point at which atoms would have no thermal energy left to give up. As matter approaches this temperature, strange things begin to happen. Gases become liquids, then solids. Certain metals lose all electrical resistance entirely and become superconductors, allowing current to flow forever without any energy loss. Certain fluids become superfluids, flowing without friction up the sides of containers and through gaps too small to see. But absolute zero itself remains permanently out of reach. To cool something down, you must remove heat from it, which means transferring that heat somewhere colder. But nothing is colder than absolute zero. There is nowhere to send the last remaining energy. Each step toward absolute zero requires more effort than the last. Laboratories have gotten extraordinarily close, within billionths of a degree. The gap keeps shrinking. The destination never arrives. And that brings us to fact 24. When you make a hot drink and leave it on a table, it will always cool down. This happens in 3 ways simultaneously. Conduction is heat moving through direct contact. The hot liquid touches the cooler cup, which touches the cooler table, and heat flows along that chain of contact. Convection is heat moving through fluid motion. Warmer liquid rises, cooler liquid sinks, creating circular currents that gradually even out the temperature throughout the cup. Radiation is heat leaving as invisible infrared light emitted by any object warmer than its surroundings, requiring no medium at all. Your drink is doing all 3 at once. The surrounding air is cooler than the drink. The table is cooler. The room is cooler. Heat always moves from warmer to cooler, never the other way, until everything reaches the same temperature. Your tea was always going to lose. The second law of thermodynamics guaranteed it from the moment you poured it. Fact 25. In 1752, Benjamin Franklin flew a kite in a thunderstorm with a metal key tied to the string. He was not trying to get struck by lightning. He was trying to draw electrical charge from the clouds to prove that lightning was electrical in nature. The key collected charge from the electrified air, producing sparks when he brought his knuckle close to it. The experiment worked. Lightning is electricity, a massive discharge of electrical charge between clouds and the ground. Franklin was extraordinarily lucky to survive. 2 European scientists who attempted to replicate his experiment shortly afterward were killed. What Franklin gave the world beyond the proof was the lightning rod, a simple metal spike on a rooftop connected by a wire to the ground. Lightning, given a conducting path to follow, takes it and bypasses the building entirely. A kite, a key, a thunderstorm, and a correct idea about the nature of electricity saved countless buildings and lives in the centuries that followed. And next, fact 26. Michael Faraday was the son of a blacksmith. He had almost no formal education. He taught himself science by reading books he was given access to while working as an apprentice bookbinder as a teenager. He attended public lectures by the chemist Humphrey Davy, took detailed notes, bound them carefully, and sent them to Davy as an application for a job. Davy hired him. Faraday went on to make one of the most consequential discoveries in the history of physics. In 1831, he showed that moving a magnet near a wire caused an electric current to flow in the wire. Electricity and magnetism previously thought to be separate phenomena were deeply connected. A changing magnetic field produces an electric current. This is electromagnetic induction. It is the operating principle behind every electrical generator ever built. Every power station in the world, coal, gas, nuclear, wind, hydro, works by spinning a magnet near coils of wire. The entire electrical grid that runs modern civilization runs on the discovery made by a blacksmith's son who had no university education. Fact 27. Electricity is the movement of electrons through a conductor. Electrons are tiny negatively charged particles that orbit the nucleus of every atom. In certain materials, particularly metals, some electrons are loosely attached and can move freely from atom to atom. Apply a force and they flow in a current. Three quantities describe this flow. Current is the amount of charge passing a point per second, measured in amperes. Voltage is the pressure driving the electrons forward, measured in volts. Resistance is how much the material opposes the flow, measured in ohms. The relationship between them is simple. A useful way to picture it is water in a pipe. Current is how much water flows through. Voltage is the water pressure pushing it. Resistance is the narrowness of the pipe. Higher pressure pushes more water through. A narrower pipe restricts the flow. These three quantities and their relationship, described by Ohm's law, underlie the design of every electrical circuit ever built, from the simplest battery and bulb to the most complex computer processor. Moving on to fact 28. In the 1860s, a Scottish mathematician named James Clerk Maxwell sat down and wrote 4 equations. Those 4 equations described everything known about electricity and magnetism in a single unified mathematical framework. Electric fields, magnetic fields, how each one is produced, how each one changes the other. Maxwell unified 2 forces that had previously been studied separately and showed they were aspects of a single phenomenon, electromagnetism. Einstein kept a photograph of Maxwell on his office wall alongside portraits of Newton and Faraday. He considered Maxwell's work the most profound change in physics since Newton. The equations themselves are compact and elegant, but their consequences extend to radio waves, television signals, wireless communication, X-rays, and visible light. All of these are the same thing, electromagnetic waves of different frequencies, all described by the same 4 equations Maxwell wrote in the 1860s. He did not know about radio or television. He was simply following the mathematics wherever it led. And here is fact 29. When Maxwell finished his equations, he noticed something remarkable. The mathematics predicted the existence of waves made of oscillating electric and magnetic fields traveling through space. He calculated the speed at which these waves would travel. The number that came out was approximately 300,000 kilometers per second. Maxwell recognized that number immediately. It was the measured speed of light. The conclusion was direct and stunning. Light is an electromagnetic wave, not something like an electromagnetic wave. Light is one. Maxwell had not designed his equations to say anything about light. He had been working purely on electricity and magnetism, but the mathematics, followed honestly, produced the speed of light as a consequence. This meant that visible light, whatever makes a fire warm from a distance, and whatever carries a radio signal are all the same kind of thing, different frequencies of the same electromagnetic wave. Maxwell proved it without building anything or running a single experiment. Pure mathematics revealed the nature of light. Fact 30. In the late 1880s, 2 visions of how to deliver electricity to homes and cities went to war. Thomas Edison had built a direct current system, DC, where electricity flows in one direction continuously. Nikola Tesla, working with the industrialist George Westinghouse, championed alternating current, AC, where the current reverses direction many times per second. AC had a significant practical advantage. It could be transmitted over long distances at high voltage and then stepped down for home use using transformers. DC could not do this efficiently. Edison, rather than acknowledge the superiority of AC, launched a public relations campaign to convince the public that AC was dangerous. His team publicly electrocuted animals using alternating current, including in 1903 a circus elephant named Topsy to demonstrate its lethal potential. The campaign failed. AC won. It won because the physics was better. Alternating current is what comes out of every wall socket in the world today. Edison was a brilliant inventor. On this particular question, the physics sided with Tesla, and that brings us to fact 31. A compass needle points north because the Earth itself is a giant magnet. Deep inside the planet, the outer core is made of liquid iron and nickel. This molten metal moves in slow convection currents, driven by heat from the inner core. Moving electrical charges generate magnetic fields. The moving liquid iron generates a magnetic field that extends far out into space around the Earth, called the magnetosphere. The compass needle aligns with this field, but here is something most people do not know. The geographic North Pole, the point around which the Earth rotates, and the magnetic North Pole are not in the same place. The magnetic North Pole is currently located in northern Canada, several hundred kilometers from the geographic pole. It also moves over time, drifting gradually as the patterns in the liquid outer core shift. Compasses have always pointed to magnetic north, not true north. Navigators have always had to account for the difference. The Earth's magnetic field has also flipped completely, north becoming south and south becoming north, hundreds of times over geological history. It will likely flip again. Fact 32. Sound is not a thing that travels. It is a disturbance that travels. When something vibrates, it pushes the air molecules next to it. Those molecules push the ones next to them. That push travels outward in all directions as a wave of alternating compression and expansion. Your ear has a thin membrane called the eardrum stretched across the ear canal. When those pressure waves arrive, they push the eardrum back and forth in exactly the same pattern as the original vibration. 3 tiny bones amplify that movement and pass it to a fluid-filled spiral chamber called the cochlea. Fine hairs inside the cochlea bend in response and send electrical signals to the brain. The brain interprets those signals as sound. Silence is not emptiness. Silence is the absence of pressure variation. A perfectly silent room is one where the air pressure at your eardrum is completely steady, not pushing or pulling at all. True silence is extraordinarily rare. Almost every environment has some vibration, some pressure variation, something the ear is quietly receiving. And next, fact 33. When an ambulance is moving towards you, each sound wave it produces is compressed slightly because the source is chasing its own waves. The waves arrive at your ears more frequently than they would from a stationary source. Higher frequency means higher pitch. As the ambulance passes and moves away, the opposite happens. Each wave has further to travel before reaching you. The waves arrive less frequently. Lower frequency means lower pitch. That shift from high to low as the vehicle passes is the Doppler effect. Astronomers use the exact same principle to measure how fast stars and galaxies are moving. Light behaves like a wave. If a star is moving toward Earth, its light waves are compressed and shift toward the blue end of the spectrum. If it is moving away, they stretch toward the red end. By measuring how much a star's light is shifted from its expected color, astronomers can calculate its speed with considerable precision. The same physics that changes the pitch of a passing ambulance tells us how fast the universe is expanding. Fact 34. Light travels at approximately 300,000 kilometers per second. Sound travels through air at about 343 meters per second. Light is roughly 1,000,000 times faster. This gap is why you see lightning before you hear thunder. The lightning flash reaches your eyes almost instantly regardless of distance. The sound of the thunder has to travel the entire distance between the strike and your ears at a much slower pace. Every 3 seconds between the flash and the rumble represents about 1 kilometer of distance. People have used this simple calculation for generations to estimate how far away a storm is without any instruments at all. The same principle applies to watching distant fireworks, where you see the burst and wait for the boom, or watching a distant construction crew where you see the hammer fall and hear the strike a moment later. Two signals leaving the same event at the same time but arriving at very different speeds, the gap between them quietly measuring the distance in between. Moving on to fact 35. Sound needs a medium to travel through. It is a pressure wave, and pressure requires matter to push against. In space, there is no air, no medium of any kind between objects. This means space is completely and perfectly silent. The enormous explosions of supernovae, stars dying in catastrophic collapse, releasing more energy than the sun will produce in its entire lifetime, produce no sound whatsoever. There is nothing for the pressure wave to travel through. When astronauts on the moon needed to communicate, they used radio. Radio waves are electromagnetic, not mechanical. They do not need a medium. They travel through vacuum perfectly well. Two astronauts standing on the lunar surface, touching helmets, could theoretically conduct sound through the physical contact between suits, but speak into the vacuum between them, and nothing crosses the gap. Films that show dramatic sound effects during space battles are taking considerable liberties with the physics. The universe is almost entirely silent. The thin layer of atmosphere wrapped around this one planet is a rare and unusual exception, and that brings us to fact 36. Every object has a natural frequency at which it prefers to vibrate. Push it at that frequency and the vibrations build on each other, growing larger with each cycle. This is resonance. A trained singer can shatter a wine glass by producing a note at exactly the glass's natural frequency. The sound waves push the glass at its own resonant frequency. The vibrations amplify, and the glass eventually cannot absorb any more energy and breaks. The same principle destroyed the Tacoma Narrows Bridge in Washington State in 1940. Wind flowing over the bridge created oscillations that matched the bridge's natural frequency. The oscillations grew. The bridge began twisting dramatically. Within hours, it collapsed entirely. Engineers now design bridges specifically to avoid resonance with common wind frequencies. Your phone buzzes differently on a wooden table than on a glass surface because each surface has different natural frequencies that the vibration interacts with. Resonance is everywhere once you know to look for it. In bridges, in wine glasses, in musical instruments, in the way a washing machine shakes when the load is uneven. Fact 37. Light is one of the most studied things in physics and also one of the most genuinely strange. For centuries, scientists argued about whether it was a wave or a stream of particles. Newton believed it was particles. Others believed it was waves. Experiments kept producing evidence for both sides. Then in the early 20th century, something deeply uncomfortable became clear. Light is both, depending on how you look at it. When light travels through space, it behaves like a wave, spreading out, interfering with itself, bending around obstacles. But when light interacts with matter, when it hits a surface or gets absorbed by an atom, it behaves like a particle, a discrete packet of energy called a photon. This is wave-particle duality, and it is not a limitation of our understanding. It is a genuine property of light itself. Light does not secretly have one true nature that we have failed to identify. It has both natures simultaneously and reveals one or the other depending on the situation. This was deeply troubling to physicists in the early 20th century. Most eventually accepted it not because it made sense, but because every experiment confirmed it without exception. And next, fact 38. Visible light, the light your eyes can detect, occupies an almost absurdly narrow band of the full electromagnetic spectrum. The spectrum runs from radio waves at one end, with wavelengths measured in kilometers, all the way to gamma rays at the other end, with wavelengths smaller than an atomic nucleus. In between, in order of increasing frequency, are microwaves, infrared, visible light, ultraviolet, and X-rays. Your eyes respond to a tiny slice in the middle. Everything outside that slice is invisible to you but physically real and constantly present. The room you are in right now is filled with radio waves carrying signals from dozens of stations. It is filled with infrared radiation from every warm object in it. It is bathed in microwave signals from distant communication towers. You cannot see any of it. The visible spectrum exists because it corresponds to the frequencies of light most abundantly produced by the sun and not blocked by Earth's atmosphere. Evolution built eyes sensitive to the light that was actually available. Everything else in the spectrum remained invisible simply because seeing it offered no survival advantage. Fact 39. The sky is blue because of the way sunlight interacts with the atmosphere. Sunlight contains all colors. When it enters the atmosphere, it collides with nitrogen and oxygen molecules. These small molecules scatter shorter wavelengths of light, the blue end of the spectrum, much more effectively than longer wavelengths like red and orange. Blue light bounces off molecules in every direction across the entire sky. Look anywhere overhead and scattered blue light reaches your eyes. At sunset, the geometry changes. The sun is near the horizon, and its light must travel through a much thicker slice of atmosphere to reach you. By the time it arrives, most of the blue has already scattered away in other directions. What remains is the longer wavelengths, the reds and oranges, which travel through more atmosphere without scattering as much. Same sunlight, same atmosphere, different path length through it. The color changes completely. The blue of noon and the red of sunset are the same phenomenon seen from different angles. Moving on to fact 40. When you stand in front of a mirror, your left hand appears to be on the right side of your reflection. Left and right seem reversed, but your head is still at the top and your feet at the bottom. Up and down are not reversed. Why does a mirror reverse left and right, but not up and down? The answer is that it does neither. A mirror reverses front and back. It takes the direction pointing away from you and flips it towards you. Your reflection is not left-right reversed. It is depth reversed, flipped along the axis pointing into the mirror. The apparent left-right reversal happens because you instinctively imagine rotating yourself to face the same direction as your reflection, the way you would if you walked around to face another person. That mental rotation is what creates the sense of reversal. The mirror itself made no such rotation. It simply bounced the light back. The confusion is entirely inside the brain interpreting the image, not in the physics of the reflection itself. And here is fact 41. The speed of light in a vacuum is approximately 299,792 kilometers per second. Nothing with mass can reach it. This is not an engineering limitation. It is a fundamental feature of the universe. As an object with mass accelerates toward the speed of light, it requires more and more energy to accelerate further. As it approaches the speed of light, the energy required approaches infinity. You could never supply enough. This is a consequence of special relativity, which we will cover properly shortly. But even approaching the speed of light produces remarkable effects. Time passes more slowly for a fast-moving object relative to a stationary observer. Distances contract in the direction of motion. These are not illusions. They are real physical changes in how time and space behave at high velocities. The speed of light is the universe's absolute speed limit. It is also the reason the universe has a horizon. Light from sufficiently distant regions has not had time to reach us since the Big Bang. Whatever lies beyond that horizon is permanently invisible, regardless of any telescope ever built. And that brings us to fact 42. An ordinary light bulb emits light in all directions at many different wavelengths simultaneously. The photons leave at random times heading in random directions. A laser is completely different. In a laser, atoms in a medium, a gas, crystal, or semiconductor are excited to a higher energy state. When one atom releases a photon, that photon triggers neighboring excited atoms to release photons of exactly the same wavelength, traveling in exactly the same direction, perfectly synchronized. This is stimulated emission, the process that gives laser its name. Light amplification by stimulated emission of radiation. The result is a beam of light where every photon is identical, coherent, and traveling together. This coherence is what makes laser light so different from ordinary light. It can be focused to an extraordinarily small point, carry enormous energy density, and travel long distances without spreading. What began as a laboratory curiosity in 1960 now reads, your supermarket barcodes, plays your music, performs eye surgery, measures the distance to the moon, and cuts through steel. Fact 43. Albert Einstein was 16 years old when he asked himself a question that would eventually break Newtonian physics. What would it look like to ride alongside a beam of light? If you could travel at the speed of light next to a light wave, would the wave appear frozen beside you, the way a car on a motorway appears still when you match its speed? Maxwell's equations said no. They said light always moves at the same speed regardless of the observer. But Newton's physics said speeds should add and subtract normally. Both could not be right. Einstein sat with this contradiction for 10 years. He was not a professor. He was a junior clerk at a patent office in Bern, Switzerland, reviewing other people's inventions during the day and thinking about light in whatever time remained. In 1905, at 26, he published 4 papers that each would have made most physicists famous for a lifetime. One of them contained special relativity. The question he had asked at 16, what does a light wave look like from alongside it, turned out not to have a simple answer. It turned out to require rebuilding the foundations of physics from scratch. And next, fact 44. Special relativity rests on just 2 assumptions. First, the laws of physics are the same for everyone moving at a constant velocity, regardless of how fast they are moving or in what direction. There is no special stationary point in the universe. Second, the speed of light in a vacuum is the same for every observer, regardless of the motion of the source or the observer. These 2 statements sound reasonable. What follows from them is not. If the speed of light is constant for everyone, then time and space cannot be constant. They must adjust to keep the speed of light fixed. 2 observers moving at different speeds will measure different amounts of time passing between the same 2 events. They will measure different distances between the same 2 points. Neither is wrong. They are both correct within their own frames of reference. Space and time are not fixed backgrounds against which events happen. They are flexible, stretchable quantities that adjust depending on the motion of the observer. Newton's universe had one absolute time ticking at the same rate everywhere for everyone. Einstein's universe has no such thing. Time is personal. Fact 45. One of the direct consequences of special relativity is time dilation. The faster you move, the slower time passes for you relative to a stationary observer. This is not a perceptual trick. Clocks actually run slower when moving. At everyday speeds, the effect is too small to notice. At speeds approaching light, it becomes dramatic. A traveler moving at 90% of the speed of light would age significantly more slowly than someone who stayed behind. Return from a long enough journey at high enough speed, and the person who stayed home would be decades older. This is not science fiction. It has been measured directly using atomic clocks on aircraft and satellites. GPS satellites orbit Earth at high speed and at altitude. Both speed and altitude affect how time passes for them relative to clocks on the ground. The satellites experience time passing at a slightly different rate. Engineers must correct for this constantly. Without the correction, GPS systems would accumulate errors of several kilometers per day. Every time you use navigation on your phone, the software is quietly accounting for Einstein's time dilation to give you an accurate position. Moving on to fact 46, time dilation has a companion effect. Length contraction. An object moving at high speed is physically shorter in the direction of motion than it would be at rest. Not shorter because it is compressed by air resistance or any physical force. Shorter because of the geometry of space-time itself at high velocities. A spacecraft traveling at 90% of the speed of light would be measured by a stationary observer as significantly shorter than its rest length. The crew inside would measure it as normal. Both measurements are correct. This seems paradoxical, but the paradox dissolves when you accept that there is no single universal measurement of length any more than there is a single universal measurement of time. Length, like time, depends on the relative motion between the measurer and the measured. At the speeds of everyday life, the contraction is immeasurably small. At speeds approaching light, it becomes significant. The universe does not have fixed, rigid distances built into it. Space itself is as flexible as time. And here is fact 47. E equals mc squared is the most famous equation in physics, and possibly in all of science. It says that energy and mass are the same thing expressed differently. E is energy, m is mass, c is the speed of light. Because the speed of light is an enormous number, and the equation squares it, even a tiny amount of mass corresponds to a staggering amount of energy. 1 kilogram of mass, if converted entirely to energy, would release approximately the same energy as 21 megatons of TNT. The sun converts about 4 million tons of mass into energy every single second through nuclear fusion, and has been doing so for 4.5 billion years. Nuclear weapons work by converting a small fraction of their mass into energy. Even a fission bomb converts less than 1% of its mass. The equation does not tell you how to release that energy. It tells you that the energy is there, locked inside mass, waiting. The conversion factor is the speed of light squared. That number is so large that mass and energy are not just related. They are, at the deepest level, the same thing. Fact 48. Special relativity dealt with objects moving at constant velocities. 10 years later, Einstein published General Relativity, which handled acceleration and gravity. The central idea is radical. Gravity is not a force in the way Newton described it. It is a curvature of space-time caused by mass. Imagine space-time as a stretched rubber sheet. Place a heavy ball on it, and the sheet curves downward around the ball. A smaller ball rolling nearby follows the curve in the sheet and spirals inward. It appears to be attracted to the heavy ball, but it is not being pulled by any force. It is simply following the straightest possible path through curved space. This is what planets do around the sun. They are following the straightest possible paths through space-time curved by the sun's mass. What feels like gravity is the geometry of space-time itself. General relativity predicted several things Newton's theory could not. That light bends when passing near massive objects. That time runs slower in stronger gravitational fields. That the universe is not static, but dynamic, expanding or contracting. All of these predictions have been confirmed experimentally with extraordinary precision. And that brings us to fact 49. In May 1919, there was a total solar eclipse visible from parts of Africa and South America. The British astronomer Arthur Eddington led 2 expeditions to photograph stars near the edge of the sun during the eclipse. The moon would block the sun's light just long enough to photograph stars that would normally be invisible in its glare. General relativity predicted that the sun's mass would bend the light from those stars, shifting their apparent positions slightly. Newton's theory also predicted a bending effect, but half the size. If Einstein was right, the stars would appear in slightly different positions than expected. Eddington's photographs showed exactly the shift Einstein had predicted. The results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The next morning, Einstein was on the front page of newspapers around the world. He had been quietly known in scientific circles before that evening. By the following morning, he was famous everywhere. He remained so for the rest of his life. And finally, in this cluster, Fact 50. Black holes were predicted directly by Einstein's equations of general relativity, published in 1915. Einstein himself did not believe they could actually exist. They seemed too extreme. A black hole forms when enough mass is concentrated in a small enough space that the curvature of space-time becomes infinite. The gravitational pull becomes so strong that nothing, not matter, not light, can escape once it crosses a boundary called the event horizon. From outside the event horizon, a black hole is invisible. No light escapes to reveal it. Time near a black hole runs dramatically slower than far from it. At the event horizon itself, time as measured by a distant observer effectively stops. An astronaut falling into a black hole would not notice anything unusual as they cross the horizon, but to an observer watching from a safe distance, the astronaut would appear to slow down, redden, and freeze at the edge, never quite crossing it, suspended there forever. Both descriptions are physically correct simultaneously. Black holes remained theoretical for decades. We now know they exist throughout the universe and that most large galaxies, including our own, have one at their center. Fact 51. In the late 1800s, physicists were trying to calculate how much energy a heated object should radiate at different frequencies. Classical physics gave a clear prediction. As frequency increased toward the ultraviolet end of the spectrum, the predicted energy should rise without limit, approaching infinity. This was obviously wrong. No object radiates infinite energy. Hot objects glow red, then orange, then white, but they do not produce infinite ultraviolet radiation. The prediction was so catastrophically incorrect that physicists called it the ultraviolet catastrophe. It was not a small discrepancy. It was a fundamental failure of classical physics to describe something as ordinary as a glowing piece of metal. The assumption that energy could exist in any amount, flowing continuously in whatever quantity the situation required, turned out to be false. Fixing it would require abandoning one of the most basic beliefs in all of physics. And next, fact 52. Max Planck was a conservative physicist who deeply respected classical traditions. He was not looking to start a revolution. In 1900, working on the ultraviolet catastrophe, he found that the only way to make the equations match observed reality was to assume energy was not continuous, that it came in discrete packets of a fixed minimum size. He called these packets quanta. The size of each packet was determined by a tiny number now called Planck's constant. Planck was deeply uncomfortable with his own solution. He spent years trying to reinterpret it as a mathematical trick rather than a physical reality. He could not. Energy really does come in discrete packets. The continuous flow assumed by classical physics does not exist at the smallest scales. Planck had accidentally dismantled a cornerstone of physics while trying to preserve it. Fact 53. When light shines on certain metals, electrons are knocked off the surface. The puzzling part was that the energy of the ejected electrons did not depend on the brightness of the light. It depended only on the frequency. Dim light of a high enough frequency knocked out electrons. Bright light below a certain frequency knocked out nothing at all. Einstein proposed that light was not a continuous wave, but was made of discrete particles, each carrying a fixed amount of energy determined by its frequency. These particles are called photons. A high-frequency photon carries enough energy to eject an electron. A low-frequency photon does not, regardless of how many arrive. Einstein received the Nobel Prize for this discovery in 1921, not for relativity, for the photoelectric effect. Moving on to fact 54. Classical physics predicted that electrons orbiting a nucleus should continuously radiate energy and spiral inward, causing every atom to collapse within a fraction of a second. Atoms are obviously stable. In 1913, Niels Bohr proposed a solution. Electrons occupy specific fixed energy levels, like rungs on a ladder. They jump between rungs by absorbing or emitting a photon of exactly the right energy. Between the rungs, they simply do not exist. When an electron drops from a higher level to a lower one, it emits a photon whose color corresponds to the energy difference. Different elements have different energy level arrangements and therefore emit different colors. This is why fireworks are different colors. Copper burns blue-green, sodium burns yellow, strontium burns red. Each color is the light emitted by electrons jumping between specific energy levels in specific atoms. And here is fact 55. The double-slit experiment is the most disturbing experiment in physics. Fire electrons one at a time at a barrier with two narrow slits. Each electron hits the screen behind and leaves a single dot. After many electrons have passed through, a pattern builds on the screen. It is an interference pattern, the kind produced by waves overlapping, but each electron traveled individually. There was nothing to interfere with. The only explanation is that each electron went through both slits simultaneously and interfered with itself. When physicists set up detectors to observe which slit each electron actually used, the interference pattern disappeared instantly, and the electrons behaved like ordinary particles. The act of observing which path was taken destroyed the wave behavior entirely. The experiment has been repeated countless times with identical results. The conclusion is unavoidable even if it remains deeply uncomfortable. Fact 56. In quantum mechanics, a particle does not have a definite position before it is measured. Instead, it has a wave function, a mathematical description of the probability of finding it in any particular state. The particle is not secretly in one place we have failed to locate. It genuinely exists as a spread of probabilities until measurement occurs. This is superposition. A particle can be in multiple states simultaneously, not because we are ignorant of which state it is in, but because the question has no answer until measurement. When a measurement is made, the wave function collapses to a single outcome. What causes this collapse and what measurement actually means at a physical level are questions physicists still argue about. The mathematics is settled and extraordinarily precise. The interpretation remains genuinely contested. And next, fact 57. In 1935, Erwin Schrödinger proposed a thought experiment to highlight what he saw as an absurdity in quantum mechanics. Place a cat in a sealed box with a tiny amount of radioactive material, a detector, and a vial of poison. If the detector registers a decay, the vial breaks and the cat dies. Quantum mechanics says the radioactive atom exists in superposition until observed. If that superposition extends to everything connected to it, the cat is simultaneously alive and dead before you open the box. Schrödinger intended this as a criticism, not a genuine claim. He was pointing out that applying quantum superposition to large everyday objects produced nonsense. The thought experiment is widely misunderstood. It was an argument that something was missing from the theory, not a statement that cats can actually be alive and dead at the same time. Moving on to fact 58. In 1927, Werner Heisenberg proved that you cannot know both the position and the momentum of a particle precisely at the same time. The more precisely you measure one, the less precisely you can know the other. This is not a limitation of measuring instruments. The uncertainty is built into the nature of reality itself. A particle with a precisely defined position has a completely undefined momentum. A particle with a precisely defined momentum is spread across all of space. The two quantities are fundamentally incompatible. Heisenberg's uncertainty principle sets a hard limit on how much can ever be known about a quantum system. This limit is not a practical obstacle to better technology. It is a feature of the universe. At the quantum scale, perfect knowledge of a physical system is not just difficult, it is mathematically impossible. And here is fact 59. Quantum entanglement occurs when two particles interact such that their quantum states become linked regardless of the distance between them. Measure one particle and you instantly know something about the other, even across the universe. Einstein found this deeply troubling and called it spooky action at a distance. He argued there must be hidden information carried by the particles that determined outcomes in advance. In 1964, John Bell devised a mathematical test to distinguish between Einstein's explanation and genuine entanglement. Experiments from the 1970s onward consistently confirmed genuine entanglement. Einstein was wrong. The connection is real. This does not allow information to travel faster than light because each individual measurement outcome is still random, but the correlation between the two outcomes is real, instantaneous, and has no classical explanation whatsoever. Fact 60. Classical physics says a particle cannot pass through a barrier without enough energy to overcome it. Quantum mechanics disagrees. Because a particle's position is described by a wave function spread across space, there is a small but real probability of finding it on the other side of the barrier without enough energy to climb over. This is quantum tunneling. Nuclear fusion in the sun requires hydrogen nuclei to get close enough to merge. Classically, they lack sufficient energy to overcome their mutual electrical repulsion. Quantum tunneling allows them through anyway, making fusion possible and keeping the sun burning. Without tunneling, there would be no sunlight. Flash memory in USB drives and solid-state hard drives works by moving electrons through a thin insulating barrier via tunneling. Every time you save a file, quantum mechanics is doing the work. And that brings us to fact 61. The measurement problem is one of the deepest unresolved questions in physics. Quantum mechanics says that before measurement, a system exists in superposition. Measurement causes collapse to a single outcome. But what counts as a measurement? The mathematics does not specify. Different interpretations answer this differently while remaining mathematically identical. The Copenhagen interpretation says collapse simply happens when measurement occurs, and asking what happens before is meaningless. The many worlds interpretation says the wave function never collapses, and every possible outcome occurs in a branching universe. Physicists have argued about this since the 1920s. No experiment has distinguished between interpretations because they all make identical predictions. The equations of quantum mechanics are the most precisely tested in all of science. What they mean about the nature of reality remains genuinely open. Fact 62. In 1896, Henri Becquerel stored uranium salts in a drawer on top of a wrapped photographic plate. The drawer was dark. No light could reach the plate. When he developed it anyway, he found it had been exposed. Something from the uranium had passed through the wrapping without any external energy source and without anything being done to the uranium at all. Becquerel had discovered radioactivity entirely by accident. Marie Curie became obsessed with understanding why. She coined the word radioactivity and discovered that it came from inside the atom itself, not from any chemical reaction between atoms. This meant atoms were not the unchanging objects everyone assumed. She identified two new radioactive elements, polonium and radium, working in a leaking shed with inadequate equipment. She did not know the radiation was slowly destroying her health. And next, fact 63. Radioactive materials emit three distinct types of radiation. Alpha radiation consists of clusters of 2 protons and 2 neutrons fired from an unstable nucleus. Alpha particles are large and slow. A sheet of paper stops them. They are dangerous only if inhaled or ingested. Beta radiation consists of fast electrons ejected from the nucleus. Beta particles travel further and require a few millimeters of aluminum to stop them. Gamma radiation is not a particle, but a high-energy electromagnetic wave. Gamma rays travel at the speed of light and penetrate deeply into matter. Stopping them requires several centimeters of lead or meters of concrete. The same penetrating property that makes gamma radiation dangerous also makes it medically useful. It can reach deep inside the body, which is why it is used in cancer treatment and medical imaging. Fact 64. Nuclear fission splits a heavy atomic nucleus into smaller pieces. When a neutron strikes a uranium nucleus, it becomes unstable, splits, and releases energy along with additional neutrons. Those neutrons strike other nuclei, causing further splits and releasing more neutrons. This is a chain reaction. If enough fissile material is present, a critical mass, the chain reaction becomes self-sustaining and releases enormous energy. In a nuclear weapon, this happens without restraint. In a nuclear power plant, control rods absorb excess neutrons, keeping the reaction steady. That controlled reaction produces heat, boils water, creates steam, and drives turbines to generate electricity. The physics is identical in both cases. The difference is entirely one of control. Moving on to fact 65. Nuclear fusion joins light atoms together rather than splitting heavy ones apart. When hydrogen nuclei merge into helium, the result weighs slightly less than the original components. That missing mass becomes energy. Fusion releases several times more energy per kilogram than fission and produces no long-lived radioactive waste. It is what powers the sun, which fuses around 600 million tons of hydrogen every second. Replicating this on Earth requires temperatures exceeding 100 million degrees Celsius. No physical container can hold plasma that hot, so powerful magnetic fields are used instead. Progress has been made, but the goal remains elusive. As the joke in the field goes, practical fusion power has been 30 years away for the past 60 years. And here is fact 66. Radioactive atoms decay at a fixed statistical rate. You cannot predict when any individual atom will decay, but given a large enough sample, the fraction that decays in any time period is constant. The half-life is the time it takes for half a sample to decay. Carbon-14 has a half-life of about 5,730 years. Living organisms continuously absorb carbon-14 from the atmosphere. When an organism dies, the absorption stops and the carbon-14 decays at its fixed rate. Measuring how much remains tells scientists how long ago the organism died. This works reliably up to around 50,000 years. For older materials, isotopes with longer half-lives are used. The age of the Earth itself, 4.5 billion years, was determined using the known decay rates of uranium isotopes. And that brings us to fact 67. Marie Curie is the only person in history to win Nobel Prizes in 2 different scientific disciplines, physics in 1903 and chemistry in 1911. She was the first woman to win a Nobel Prize and still the only woman to have won 2. Her notebooks from the 1890s are still radioactive today. They are stored in lead-lined boxes in the French National Library. Researchers who wish to examine them must sign a waiver and wear protective equipment. Curie died in 1934 from a plastic anemia caused by decades of radiation exposure. She carried radioactive isotopes in her pockets and kept radium on her bedside table because she found its faint glow beautiful. She knew the radiation was harmful. She continued anyway. Fact 68. The Big Bang was not an explosion in space. It was an expansion of space itself. Around 13.8 billion years ago, everything that exists, all matter, all energy, all of space, was compressed into an extraordinarily hot and dense state. Space then began expanding rapidly and has been expanding ever since. The evidence is solid. Galaxies are moving away from us in every direction. The further away a galaxy is, the faster it recedes. Running this expansion backward leads to a single point of origin. Additionally, the universe is filled with a faint background radiation that matches precisely what the Big Bang model predicts. For decades, many physicists resisted the idea, preferring a steady-state universe that had always existed. The Belgian priest and physicist Georges Lemaitre proposed the expanding universe first in 1927. He was largely ignored until the observational evidence became impossible to dismiss. And next, fact 69. In 1964, 2 engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were testing a large microwave antenna. They kept detecting a faint, persistent hiss coming from every direction in the sky simultaneously. They checked their equipment repeatedly. They found pigeons nesting in the antenna and removed them. They cleaned out what they politely described in their notes as white dielectric material, which was pigeon droppings. The hiss remained. They eventually contacted nearby Princeton physicists who were actively searching for exactly this signal. What Penzias and Wilson had found was the cosmic microwave background, the faint afterglow of the Big Bang itself, the thermal radiation left over from when the universe first cooled enough for light to travel freely. It fills the entire universe uniformly. It was predicted theoretically years before they found it. They won the Nobel Prize in 1978. The pigeons were not acknowledged. Fact 70. Stars are born inside vast clouds of gas and dust called nebulae. Gravity pulls regions of the cloud inward. As material falls together, the cloud collapses, heats up, and the pressure at the center rises. When the temperature at the core reaches about 10 million degrees Celsius, hydrogen nuclei begin moving fast enough to overcome their electrical repulsion and fuse together. Nuclear fusion ignites. The outward pressure of the energy released by fusion balances the inward pull of gravity. A star is born. This balance between gravity pulling inward and radiation pressure pushing outward is what defines a star's life. Larger stars burn hotter and faster, exhausting their fuel in millions of years. Smaller stars burn cool and slow, lasting tens of billions of years. Our Sun is a medium-sized star about halfway through its roughly 10 billion year lifespan. It has been burning steadily for 4.6 billion years. Moving on to fact 71. What happens when a star dies depends entirely on its mass. A star like our Sun will eventually exhaust its hydrogen fuel, expand into a red giant large enough to engulf the inner planets, and then shed its outer layers, leaving behind a dense, slowly cooling remnant called a white dwarf. Stars several times more massive than the Sun end more dramatically. The core collapses suddenly under gravity, triggering a supernova explosion that briefly outshines entire galaxies. What remains depends on the original mass. A moderately massive star leaves a neutron star, an object the size of a city, but with more mass than the Sun, so dense that a teaspoon of its material would weigh billions of tons. The most massive stars leave behind black holes. Every atom of carbon, oxygen, iron, and gold in your body was forged inside a star and scattered across space when that star died. And here is fact 72. In the 1920s, Edwin Hubble was measuring the distances to faint smudges of light in the sky that astronomers called nebulae. He established that these smudges were not clouds of gas inside our own galaxy, but entirely separate galaxies, each containing billions of stars at enormous distances from us. Then he noticed something remarkable. Almost all of them were moving away from us, and the further away they were, the faster they were receding. This relationship, now called Hubble's law, meant the universe was expanding, every galaxy moving away from every other galaxy as the space between them stretches. This does not mean we are at the center of the universe. An observer in any galaxy would see the same thing. The expansion has no center. It is the fabric of space itself, stretching uniformly in all directions simultaneously. Fact 73. When astronomers calculate how much gravity is needed to hold galaxies together and keep galaxy clusters from flying apart, the answer is far more than the visible matter can provide. Stars, gas, dust, everything we can detect accounts for only a fraction of the gravitational pull required. The rest comes from something that emits no light, reflects no light, and interacts with ordinary matter only through gravity. Physicists call it dark matter. It makes up approximately 27% of the total content of the universe. We have never detected a dark matter particle directly. Every experiment designed to catch one has so far returned nothing. We know it exists because of what it does to the things around it. Its gravitational fingerprint is everywhere. Its actual identity remains one of the biggest open questions in modern physics. And next, fact 74. Dark energy is stranger still. In 1998, astronomers studying distant supernovae expected to find that the expansion of the universe was slowing down, pulled back gradually by gravity. Instead, they found the opposite. The expansion is accelerating. Something is pushing space apart faster and faster over time. That something is called dark energy. It makes up approximately 68% of everything in the universe. Unlike dark matter, dark energy does not clump around galaxies. It appears to be a property of space itself, present everywhere uniformly, growing in total amount as space expands. We have no idea what it actually is. It does not fit neatly into any existing theory. The discovery won the Nobel Prize in 2011. The scientists who found it described it as the most surprising result of their careers. The universe is mostly made of things we cannot explain. Moving on to fact 75. The observable universe is approximately 93 billion light-years across. This is not the full size of the universe, only the portion from which light has had time to reach us since the Big Bang. Light travels at a finite speed. The universe has existed for a finite time. There is therefore a boundary, called the cosmic horizon, beyond which nothing is visible regardless of telescope size or technology. What lies beyond that horizon is unknown and in principle unknowable from our position. The universe beyond may extend infinitely, or it may eventually curve back on itself. Current measurements suggest it is at minimum vastly larger than the observable portion. Every galaxy, every star, every planet we have ever observed or ever could observe occupies a bubble 93 billion light-years wide inside something almost certainly much larger. And that brings us to fact 76. Physics offers several possible endings for the universe, and all of them happen on timescales that make the current age of the universe seem brief. In the heat-death scenario, the universe expands forever. Stars burn out one by one over trillions of years. Black holes slowly evaporate over timescales, with more zeros than can be written in this script. Eventually, the universe reaches a state of maximum entropy, uniform temperature, no usable energy remaining, nothing happening anywhere, forever. In the Big Rip scenario, dark energy grows stronger over time until it tears apart galaxies, then solar systems, then planets, then atoms. In the Big Crunch scenario, expansion eventually reverses and everything collapses back together. Current evidence favors heat death. The universe appears to be expanding forever and accelerating as it does so. The ending will be very slow, very cold, and very quiet. Fact 77. The Standard Model is the most successfully tested theory in the history of science. It describes all known fundamental particles and 3 of the 4 fundamental forces. It organizes particles into 3 categories: quarks, which make up protons and neutrons; leptons, which include electrons and neutrinos; and bosons, which carry forces between particles. The Standard Model has made predictions confirmed by experiment to extraordinary precision, in some cases accurate to more than 10 decimal places. It successfully predicted the existence of several particles before they were experimentally detected. It is not complete. It does not include gravity. It does not explain dark matter, but within its domain, it works better than any other theory in physics. It is the closest thing science has to a complete description of what matter is made of and how the fundamental forces between particles operate. And next, fact 78. For most of the 20th century, protons and neutrons were considered fundamental particles. Then experiments in the 1960s and 1970s revealed that they have internal structure. They are made of smaller particles called quarks. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Quarks have a peculiar property. They cannot exist alone. Pull 2 quarks apart, and the energy required to separate them is enough to create new quarks, which immediately bind to the originals. You never end up with a lone quark. They are always found in combinations of 2 or 3. There are 6 types of quark in total, called up, down, strange, charm, bottom, and top. The top quark, the heaviest, was not detected until 1995. Quarks are as fundamental as anything we have found so far. Whether they have internal structure of their own remains unknown. Fact 79. The Higgs boson was the last missing piece of the Standard Model. The theory predicted that fundamental particles acquire mass through their interaction with a field that permeates all of space, called the Higgs field. Particles that interact strongly with the field have more mass. Particles that do not interact with it at all, like photons, have no mass. The particle associated with this field is the Higgs boson. Peter Higgs and others predicted its existence in 1964, finding it required building the largest and most complex scientific instrument ever constructed. The Large Hadron Collider at CERN, a circular tunnel 27 kilometers in circumference beneath the Swiss-French border, accelerates protons to within a fraction of the speed of light and smashes them together. In 2012, after decades of searching, the Higgs boson was detected. Peter Higgs received the Nobel Prize in 2013. He said he never expected to live to see it confirmed. Moving on to fact 80. Every fundamental particle has a corresponding antiparticle with the same mass but opposite charge. The antiparticle of the electron is the positron. The antiparticle of the proton is the antiproton. When a particle meets its antiparticle, both are annihilated instantly, and their combined mass converts entirely to energy. This is matter-antimatter annihilation, and it is the most energy-efficient process known to physics. The deep puzzle is this: the Big Bang should have produced equal amounts of matter and antimatter. They should have annihilated each other completely, leaving nothing but energy and an empty universe. Instead, there is a universe full of matter. Something caused a slight asymmetry, roughly one extra matter particle for every billion matter-antimatter pairs. Everything that exists, every star, every planet, every atom in your body, is the leftover residue of that tiny imbalance. Why that asymmetry exists is one of the biggest unsolved problems in physics. And here is fact 81. All of physics operates through four fundamental forces. Gravity pulls masses together and operates over unlimited range, but is by far the weakest of the four. Electromagnetism governs interactions between charged particles, operates over unlimited range, and is responsible for light, chemistry, and every everyday force you experience except gravity. The strong nuclear force holds quarks together inside protons and neutrons, and holds protons and neutrons together inside nuclei. It operates only over distances smaller than an atomic nucleus, but within that range is the most powerful force in nature. The weak nuclear force governs certain types of radioactive decay, including the process that converts protons to neutrons inside stars. It operates over an even shorter range than the strong force. Three of these four forces are described within the Standard Model. Gravity stands apart, described by general relativity, and has so far resisted all attempts at unification with the other three. Fact 82. The strong nuclear force has a problem to solve. An atomic nucleus contains multiple protons packed closely together. Protons are all positively charged. Like charges repel each other, and at the distances inside a nucleus, that repulsion is enormous. Something must overcome it, or every nucleus would instantly explode. That something is the strong nuclear force, which acts between quarks and by extension between the protons and neutrons containing them. At the extremely short distances inside a nucleus, the strong force is approximately 100 times more powerful than electromagnetism. It overwhelms the repulsion and holds the nucleus together. Outside the nucleus, the strong force drops to essentially zero almost immediately. This is why atoms are mostly empty space with a tiny dense nucleus. The strong force only operates at nuclear scales. Beyond that distance, the electromagnetic repulsion goes unchallenged, and nuclei simply cannot exist. And that brings us to fact 83. General relativity describes gravity as curved spacetime and works perfectly at large scales. Quantum mechanics describes the other three forces and works perfectly at small scales. Both theories are among the most precisely confirmed in the history of science. They are also fundamentally incompatible. When physicists try to apply quantum mechanics to gravity, the mathematics produces infinities that cannot be removed. When they try to apply general relativity at quantum scales, it breaks down entirely. The universe appears to run on two separate rulebooks that contradict each other at the boundary between the very large and the very small. A theory of everything would reconcile them into a single framework. String theory and loop quantum gravity are among the leading candidates. Neither has produced a testable prediction confirmed by experiment. The unification of general relativity and quantum mechanics remains the deepest unsolved problem in theoretical physics. And here is fact 84, a gentle one. Most people assume ice is slippery because it melts under pressure, creating a thin layer of water that acts as a lubricant. This explanation appears in textbooks. It is largely wrong. The pressure required to melt ice at typical skating temperatures is far greater than a skate blade produces. The actual reason ice is slippery is that the surface layer of ice molecules is never fully locked into the crystal structure the way interior molecules are. Even well below freezing, the outermost layer of an ice surface remains partially disordered and fluid-like. This quasi-liquid layer exists without any pressure or friction at all. It is simply a property of how ice surfaces behave. When a skate blade passes over it, this layer provides lubrication. Ice is unique among common solids in having this permanently disordered surface layer. It is slippery before you even touch it. And next, fact 85. If the universe is infinite and filled with stars in every direction, then every line of sight from Earth should eventually end at the surface of a star. The entire night sky should blaze as brightly as the surface of the sun. Instead, the night sky is dark. This puzzle is called Olber's paradox. The resolution involves two things. First, the universe has a finite age, around 13.8 billion years. Light from stars further than 13.8 billion light years has not had time to reach us yet. Second, the universe is expanding. Light from distant galaxies is stretched to longer wavelengths as space expands, shifting it out of the visible range entirely. The darkness of the night sky is not simply the absence of stars. It is direct observational evidence that the universe had a beginning and has been expanding ever since. Fact 86. A boomerang returns because of two physical effects working together. The first is aerodynamic lift. A boomerang's arms are shaped like aerofoils, curved on one side and flat on the other, exactly like an aircraft wing. As the boomerang spins through the air, each arm generates lift. The second effect is gyroscopic precession. When a spinning object experiences a force, it does not move in the direction of the force. It moves at 90 degrees to it. The lift acting on the spinning boomerang causes it to turn sideways rather than simply rising. The combination of lift and precession curves the flight path into a circle that brings it back to the thrower. The boomerang must be thrown correctly with the right angle and spin rate for these effects to balance. Traditional Australian boomerangs used for hunting were not designed to return. Returning boomerangs were used for sport and practice. Moving on to fact 87. Push one end of a rigid rod and the force travels through the rod to the other end. The rod transmits compression. Now try the same thing with a rope. The rope buckles and collapses. You cannot push a rope. A rope can only transmit tension, a pulling force, not compression, a pushing force. This is because a rope has no resistance to buckling. Its fibers can slide past each other and fold when pushed. Under tension, the fibers align and pull together, transmitting force efficiently. This distinction between tension and compression runs through all of structural engineering. Cables and suspension bridges carry tension. Stone arches carry compression. Engineers choose materials based on which type of force they need to transmit. Concrete is strong in compression but weak in tension. Steel is strong in both. The reason you cannot push a rope is the same reason bridges are designed the way they are. And that brings us to fact 88. A rainbow requires three things: sunlight, raindrops, and an observer. When sunlight enters a raindrop, it slows down and bends, a process called refraction. Different colors bend by slightly different amounts because they travel at slightly different speeds through water. The light then reflects off the inside back surface of the droplet and exits, bending again as it leaves. Each color exits at a slightly different angle, spreading white sunlight into its component colors. Red exits at a shallower angle, appearing at the top of the rainbow. Violet exits at a steeper angle, appearing at the bottom. The colors always appear in the same order for this reason. You can never reach a rainbow because it is not a physical object at a fixed location. It is an optical effect that exists only relative to your position. The sun and the raindrops move toward it, and it moves with you. Fact 89. String theory proposes that the fundamental particles of nature are not point-like objects, but tiny one-dimensional vibrating strings of energy. Different vibrational modes of the same string produce different particles, the way different vibrations of a guitar string produce different notes. The theory is mathematically elegant and has one significant advantage over previous attempts at unification. It naturally includes gravity alongside the other three forces. It requires extra dimensions of space beyond the three we experience, typically 10 or 11 dimensions in total, with the extra ones curled up too small to detect. String theory has produced remarkable mathematics and has connected previously separate areas of physics. It has not yet produced a single prediction that differs from existing theories in a way that can be tested experimentally. After decades of work by thousands of physicists, it remains mathematically beautiful and physically unconfirmed. And next, fact 90. Einstein's general relativity predicted in 1916 that accelerating masses should produce ripples in spacetime itself, spreading outward at the speed of light. He doubted they would ever be detected. They were too small. In September 2015, a detector called LIGO, consisting of two L-shaped tunnels, each 4 kilometers long, located in different US states, detected a signal lasting a fraction of a second. The signal had been produced by two black holes, each roughly 30 times the mass of the Sun, spiraling together and merging 1.3 billion light-years away. The collision released more energy in that fraction of a second than all the stars in the observable universe combined. The ripple this produced moved the LIGO mirrors by less than 1,000th the width of a proton. That measurement, confirmed simultaneously at both detectors, was gravitational waves. Einstein had been right for 99 years before anyone could check. Fact 91. The laws of physics are almost entirely time-symmetric. Run any physical process backward and the equations still work. A ball bouncing, two billiard balls colliding, planets orbiting, all of these run equally well in either temporal direction mathematically. Yet time clearly moves in one direction. We remember the past and not the future. Causes precede effects. Broken glasses do not spontaneously reassemble. The only fundamental law that distinguishes past from future is the second law of thermodynamics. Entropy always increases. Some physicists believe the arrow of time is entirely a consequence of entropy. Time feels like it moves forward simply because entropy increases in that direction. The past exists as a lower entropy state and the future as a higher one. Whether time actually flows or whether past, present, and future all exist equally and only appear sequential to observers within them is a question physics has not resolved. Moving on to fact 92. Classical computers store information as bits, each either 0 or 1. Quantum computers use qubits, which can exist in superposition, representing 0 and 1 simultaneously until measured. This allows certain calculations to be performed across multiple possible states at once. For specific types of problems, particularly those involving searching large spaces of possibilities or simulating quantum systems, quantum computers can be dramatically faster than any classical machine. They are not universally faster. For most everyday computing tasks, a classical computer is equally good and far more practical. Quantum computers are extraordinarily difficult to build and maintain. Qubits are fragile and lose their quantum properties through interaction with the environment. As of now, quantum computers have demonstrated advantages only for narrow, specialized problems. The race to scale them up reliably is one of the most competitive areas in both physics and technology. And here is fact 93. Newton's gravitational constant g appears in every calculation involving gravity. It tells you how strong gravitational attraction is between two masses at a given distance. We have measured the speed of light to better than 9 significant figures. We know the charge of an electron to 10 significant figures. G we know to only about 5 significant figures, making it the most poorly measured fundamental constant in physics. The difficulty is that gravity is extraordinarily weak compared to other forces. Measuring it precisely requires isolating the tiny gravitational attraction between laboratory masses from every other vibration, electrical effect, and disturbance in the environment. Different experimental teams using different methods consistently get answers that disagree with each other slightly but persistently. The disagreements are small but real. After more than 2 centuries of trying, we still do not know the strength of gravity as precisely as we know almost anything else in physics. Fact 94. The multiverse is not science fiction. It emerges independently from several serious physical theories. The many worlds interpretation of quantum mechanics says that every quantum measurement causes the universe to branch, with every possible outcome occurring in a separate branch. Eternal inflation, an extension of Big Bang cosmology, suggests our universe is one bubble in an endlessly expanding sea of space, with other bubbles constantly nucleating as separate universes with potentially different physical laws. String theory predicts an enormous landscape of possible universes, each with different values of the fundamental constants. These are distinct proposals from different areas of physics that independently arrive at a similar conclusion. A universe containing only what we can observe may be the exception rather than the rule. The multiverse remains untestable by definition, since other universes cannot be observed. Whether an untestable proposal qualifies as physics or philosophy is a question physicists genuinely disagree about. And next, fact 95. General relativity permits solutions to its equations that describe tunnels through space-time connecting distant regions. These are wormholes. They are mathematically valid. Whether they can physically exist is a separate question entirely. Forming a stable, traversable wormhole would require exotic matter with negative energy density, something that has no confirmed physical existence. Even if such matter existed, most physicists believe quantum effects would cause any wormhole to collapse before anything could pass through it. The wormholes depicted in films as reliable shortcuts for interstellar travel are many steps beyond what the physics actually supports. What the physics supports is this: the equations do not forbid them. Every other requirement for their existence remains either unmet or unknown. They are one of those ideas that lives legitimately in the mathematics while remaining firmly out of reach of any engineering or observation. And that brings us to fact 96. We remember the past and not the future. Causes come before effects. This feels obvious, but the laws of physics do not require it. Every fundamental equation works equally well, run forward or backward in time. The one exception is entropy. Entropy increases toward the future and was lower in the past. This asymmetry is what gives time its direction. We remember the past because the past left records, low entropy imprints on the world around us, photographs, footprints, fossils. The future has left no such records because the future is higher entropy and records require order. Memory itself is a physical process, a low entropy arrangement of matter in a brain. The reason you cannot remember tomorrow is the same reason a broken glass does not reassemble. Both are consequences of the same thermodynamic arrow pointing in one direction through time. Fact 97. Richard Feynman won the Nobel Prize in Physics in 1965 for his work on quantum electrodynamics. He was also a bongo drummer who performed regularly at a strip club in Pasadena because it was the only venue that would let him play. He cracked safes at Los Alamos during the Manhattan Project for entertainment, leaving notes inside to unsettle the scientists who opened them. He taught himself to read Mayan hieroglyphics as a hobby. He gave lectures so clear and entertaining that recordings of them are still watched by physics students decades later. He believed that if you could not explain something simply, you did not fully understand it yourself. He was diagnosed with 2 rare forms of cancer late in life and faced his illness with the same curiosity he brought to everything else. When asked what dying felt like, he said he was trying to figure it out. Feynman made physics feel like the most enjoyable thing a person could spend their life doing. For him, it genuinely was. And next, fact 98. An unusual number of history's greatest physics insights arrived during periods of forced stillness. Newton developed calculus, the theory of gravity, and the nature of light during 18 months of plague isolation in his mid-20s, away from Cambridge with nothing else to do. Einstein spent 7 years as a patent clerk in Bern, a job with long quiet stretches, and produced special relativity, the photoelectric effect, and Brownian motion in a single year during that period. Stephen Hawking was diagnosed with motor neuron disease at 21 and given 2 years to live. He lived 55 more years, developed his most important work on black holes and cosmology during periods of severe physical limitation, and said the diagnosis focused him completely. Physics does not require laboratories or institutions or funding to begin. It requires a mind with a question and enough stillness to follow it honestly wherever it leads. Fact 99. Physics is not finished. The Standard Model leaves gravity out entirely. Dark matter has been inferred from its effects for decades and never directly detected. Dark energy is accelerating the expansion of the universe and remains completely unexplained. Quantum mechanics and general relativity contradict each other at the boundary between the very small and the very large, and nobody has resolved this. These are not minor loose ends. They are fundamental gaps in the picture. The universe is mostly made of things physics cannot yet explain. Every generation of physicists has believed it was close to a complete description of nature. Every generation has been surprised by what the next layer of reality contained. There is no strong reason to believe the current generation is different. The greatest discoveries in physics are probably not behind us. The questions that remain are harder than the ones already answered. That is not a problem. That is the point. And that brings us to fact 100. In 1960, the physicist Eugene Wigner wrote an essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He was puzzled by how often mathematics developed for purely abstract reasons turned out to describe physical reality with perfect precision. The same observation applies to physics itself. Faraday's investigations into electromagnetism were pure curiosity. They became the electrical grid. Maxwell's equations were abstract mathematics. They became radio, television, and wireless communication. Quantum mechanics was considered by many of its founders to be philosophical speculation about a reality too small to ever matter practically. It now underlies lasers, transistors, MRI scanners, solar cells, and every computer processor on Earth. The pattern repeats without exception. Physics pursued for its own sake, following questions because they are interesting rather than useful, keeps producing the technology that runs civilization. Curiosity has always been the most practical thing a physicist could exercise. And finally, fact 101. Somewhere around 5,000 years ago, a person stood in a field and noticed that a shadow moved. They noticed it again the next day, at the same time, in the same direction. They did not have a word for physics. They did not know they were doing science. They were simply paying attention to the world and noticing that it behaved consistently. That same impulse carried forward to Archimedes lowering himself into a bath and watching the water rise, to Galileo sitting in a cathedral counting the swings of a lamp against his own heartbeat, to Newton sitting in a garden watching something fall and wondering why it fell toward the center of the earth rather than sideways, to Faraday moving a magnet near a wire and watching a needle twitch, to a 16-year-old Einstein asking what a light wave would look like from alongside it, to Planck staring at equations that told him something he did not want to believe about the nature of energy, to two engineers in New Jersey removing pigeons from an antenna and discovering the afterglow of the beginning of the universe, to the scientists who built a tunnel 27 kilometers long beneath the Swiss countryside and listened to two black holes collide from 1 billion years away. Every phone in every pocket, every light that comes on when you flip a switch, every GPS signal that knows where you are, every medical scan that sees inside a body without opening it. Each one is a piece of frozen physics. Someone's question, followed honestly, turned into something real. The universe has been doing physics since the beginning. We have just been taking notes.